Welcome to the lesson, Performance. Welcome to the lesson, Performance. To ensure adequate margins of safety exist, the aircraft, in the prevailing conditions, is required either to take off and clear all obstacles by prescribed margins in the takeoff flight path, or stop within the remaining runway or stopway available, following failure of the critical engine. The Aircraft Flight Manual, AFM, contains performance data which complies with regulations issued by the European Aviation Safety Agency, EASA, and EU OPS. Aircraft performance can be calculated using the AFM. However, regulated takeoff weights and V1, VR, and V2 speeds can more easily be obtained from regulated performance tables. Takeoff performance data is provided in the AFM for each individual aircraft and will conform to the specific rules for which the aircraft is certificated. The AFM performance data is supplied in graphical form. However, it can be made more accessible using the regulated performance tables provided either through BAE Systems or by various agencies. The aircraft manufacturer, BAE Systems, provides aircraft performance information in the form of a computerized performance data package. This data, coupled with external factors such as airport and environmental data, is used by other organizations to produce computer software. Pilots can easily calculate regulated takeoff and landing performance by the help of this application. Here you see an example. These data, coupled with airfield data, can also be used to produce tabular outputs of regulated takeoff weights, RTOW, or regulated landing weights for operational use. The resulting charts may be customized for specific operators. A non-specific example of a regulated performance chart is used to show the calculation principle. Other charts may use a different format, but the principle should be similar. The airport and the airport identifying codes and the runway for which the chart is calculated is given at the top of the chart. The aircraft type and series is given, and the flap setting or settings, if more than one flap setting, is displayed on each page. Additional information gives the runway details: TORA, TODA, ASDA, and LDA, together with runway width, threshold, and airport elevation, and the runway slope. Also displayed is the basis of the calculation: QNH, bleed status, air brake selection, tire speed, and the lineup allowance included. The first value was subtracted from TORA and the second from ASDA. 3 lineup methods may be considered: lineup from behind the takeoff position, lineup with a 90-degree entry, and lineup with a 180-degree turnaround. The latter assumes that a backtrack has been made and a full 180-degree turnaround is made. Below the main charts for dry and wet runways are corrections, in addition to those in the main table. The minimum acceleration height is also stated. If the chart has been customized for an operator who uses standard acceleration height or altitude, this entry should indicate that the standard acceleration heights must be adjusted for an obstacle. At the bottom of the page is listed the limit code key, the identification of specific obstacles, and the turn procedure in the event of an engine failure. The ATIS informs you that runway 25 is in use. Wind from 070 degrees at 5 knots. The temperature is at 35 degrees Celsius and the QNH is at 1015 hectopascal. The QNH correction is 41 kilograms per hectopascal, and as the QNH is 2 hectopascal above standard, 82 kilograms are added to the basic RTOW of 44,010 kilograms, which is already corrected for wind and temperature. This takeoff shall be performed with air condition on engine bleed. Therefore, 2,370 kilograms have to be subtracted from the QNH corrected basic RTOW. The chart further informs via the limit code that obstacle A is limiting at a flap angle of 18 degrees. Obstacle A is 150 meters behind the runway end at a height of 15 feet. The resulting RTOW is 41,722 kilograms, which is a maximum weight and means that a takeoff at this weight is possible under the prevailing conditions from the respective airfield with maximum takeoff thrust. The V speeds at this RTOW in knots are the following. V1 is 123, VR 136, and V2 142. On long runways, the actual takeoff weight may be less than the RTOW. If the actual takeoff weight is significantly below the limiting RTOW, then the speeds VR and V2 should be found from the speed cards, and V1 should be equal to VR. If the resulting V1 is lower than that from the RTOW table, let us assume the actual takeoff weight is 38 tons. We obtain and correct a VR from the speed card of 125 knots and a V2 of 133 knots. These are significantly lower as those at RTOW from the table and are operationally used. V1 is equal to speed card VR if lower than the V1 from the RTOW table, but in our example, the speed card V1 should be 125 knots, which is above the RTOW value and thus not allowed, so our V1 is 123 knots. If the runway is wet, a speed reduction to apply the dry runway V1 from the table might have to be added if the ASDA is limiting. Alternatively, own wet runway tables exist. Enter these tables and extract the weight and speeds and apply the appropriate corrections as shown previously in our example for the dry runway. A large proportion of turbine blade life is expended during the takeoff phase due to high thrust settings and associated high temperatures. A relatively small reduction in thrust can reduce temperatures and considerably increase blade life. When the actual takeoff weight is less than the maximum RTOW, the thrust used for the takeoff may be reduced. The takeoff N1 flex setting is obtained by correcting the full thrust value of that corresponding to an air temperature T-flex, which is greater than the ambient temperature. This higher temperature is that at the proposed weight at which the takeoff would just become limited by one or other of these performance considerations. In this example, we plan a takeoff from runway 25 at standard QNH and an actual temperature of 10 degrees Celsius with 10 knots tailwind without any bleed offtakes. The actual takeoff weight is 41,000 kilograms. The RTOW is 45,360 kilograms at 10 degrees Celsius. And if a temperature of 40 degrees Celsius was assumed, we would still be able to bring out our 41 tons heavy aircraft at maximum thrust. As we now know, we do not need maximum thrust for this takeoff. The thrust may be reduced. There is a fixed reduction in thrust called N1 reduction, and the corresponding temperature is T reduction. We obtain a T reduction of approximately 22 degrees centigrade and an N1 reduction of 90.7%. From the tables in the Flight Deck Handbook, FDH, the next step would be to check if a takeoff with a T reduction is possible. It is. No limits are penetrated. If use of the standard reduced thrust is not suitable because T redo is either limiting or thrust could be usefully reduced further, a different assumed temperature may be used. This is known as T flex, and the resulting thrust setting is called N1 flex. If planning to use flexible thrust, a temperature equating to the corrected limiting weight from the R-TOW chart may now be used at the maximum value of T flex. When the highest possible value of T-flex, here 40 degrees centigrade, is used for the conditions, the takeoff is known as full flex takeoff. Lower values of T-flex may be used, but T-flex must never be less than the actual temperature, here 10 degrees Celsius. We perform the calculation according to the manufacturer procedure described in the FDH for a full flex takeoff. As we determined before, Tmax for the no-bleed takeoff is 40 degrees Celsius. We go through step 1 of the procedure, and the result is that T-flex is 40 degrees Celsius, as the term T ambient plus 50 is higher. Step 2 dictates to determine N1 ref, which equals maximum takeoff thrust, at the T-flex of 40 degrees Celsius. The so-called N1 full rate is here 92.8%. In step 3, we subtract actual temperature from flex temperature, 40 degrees Celsius minus 10 degrees Celsius, which equals 30 degrees Celsius. And in the next step, we can either solve 30 times 0.16 or use this FDH table. Delta N1 flex is 4.8% in our example. The final calculation, according step 5, generates an N1 flex of 88%. The checks, according step 6 and 7, must be performed. Use table 8.1.6 from the FDH to check the T flat is below T flex. Here the flat rate temperature is approximately 23 degrees centigrade. All checks have been done. N1 flex is correct and may be used for this takeoff. The procedure in Table 8.1.4 calculates the maximum reduction in thrust, that is the lowest value of N1 allowed for takeoff. Any value of N1 between the full flex N1 and the N1 ref for the respective takeoff may be used. Takeoff performance data on contaminated runways is provided as an appendix in the AFM, mainly presented in the form of graphs. Normally, an RTOW chart for each type of contaminant is used by operators. The table is used in the same manner as those for